all good things come to an end, but every ending is also a new beginning. Good afternoon to all the brilliant minds who have walked this 5-day journey with us. As we step into the fifth and final day of our International Online Faculty Development Program on recent trends in chemistry, organized by Department of Chemistry, New Prince Shri Bhavani College of Engineering and Technology. Our hearts are full of knowledge gained, both strength and inspiration received. Education is not the filling of a pail, but the lighting of a fire. And over the past 4 days, we have seen this fire burn brighter with every session, every discussion, and every exchange of ideas. Today is not just the final click or another meeting link in our digital classroom, but a celebration of how technology has brought minds and hearts together across distances, and also to realize the glow of our screens, which mirrored the glow of our ideas. Together, let us make this concluding day not an ending, but a milestone. Before we begin, every program find its true start when we welcome with thought and inspiration. And now, to formally open today's proceedings with the welcome address, I take great pleasure in inviting Professor Sabrina Sir to deliver the welcome address.
Thank you, ma'am. Thanks for giving me this opportunity. Dr. Vinod Kumar received the Junior Research Fellowship from the University Grant Commission for the period of 2015 to 2017. He awarded his PhD degree in chemistry from Madurai Kamaraj University. In 2017 to 18, he served as a visiting researcher at the National Taipei University of Technology from Taiwan. Dr. Vinod Kumar was honored with the Distinguished Paper Award from the Association of Chemical Sensors in Taiwan in both the 2017 year and 2018. In 2018, he also received the Best Exchange Students Award from the National Taipei University of Technology, Taiwan. From the 2020 to 2024, he advanced in his research career as a postdoctoral fellowship and research assistant professor in South Korea. At present, Dr. Vinod Kumar is a JSPS postdoc fellowship researcher in the Department of Material Science at the University of Tsukuba from Japan. And his research in Japan focuses on the design, fabrication, and evaluation of wearable biosensors by integrating biosensing system for disease detections like saliva, tears, and sweat. And he has authored over 50 research publications in leading international journals, accumulated more than 2,000 citations with a H-index of 30. He currently served as a doctoral committee member at Madurai Kamaraj University. He is also a guest editor for the Journal of Catalysis from MDPI. He has delivered guest lectures at numerous international and national conferences. Additionally, he is a potential reviewer for leading publishers including ACS, RSC, Elsewhere, and Wiley. Now, I'd like to invite Dr. Vinod Kumar to share his insights of wearable biosensors for remote health monitoring. Now, I hand it to the session to Dr. Vinod Kumar, sir. Please share your valuable lecture, sir.
Thank you, Dr. Savary. Can you hear my voice?
Yes, sir. Yes, sir. You're audible, sir, right now.
May I share the PowerPoint?
Yeah. You can share, sir.
It is visible in presentation mode?
Yes, sir. It is visible right now.
It's visible in presentation mode?
Yeah. Good, sir.
Thank you. Thank you, Dr. Savary, for giving very nice introduction about me. Thank you so much. Also, thank you for the opportunity to present this wonderful program. Myself, I am Dr. J. Vinod Kumar, currently working as a JSPS postdoctoral researcher in Department of Material Science at University of Tsukuba in Japan. Here, our group mainly focus on the development of wearable sensor devices for the monitoring of various diseases related to the various biomarkers like proteins and hormones and small molecules and some other like glucose, lactose, these kind of biological molecules. So today we will briefly discuss about some basics and what kind of research is ongoing on, like those kind of things. Very briefly, we can discuss about the outline of today of our discussion is the problems in disease diagnostics, portable chemicals and biosensors, and wearable sensors like in physical and chemical and electrical, and kind of types of wearable sensor devices and advantages, and also role of nanomaterials, especially 2D nanomaterials, and about the discussion about and summary. Up to now, all are know the with the growing world population, the increasing the diseases is increasing day by day, known and unknown diseases like dengue, cholera, and like recently the COVID-19, and also some these are infectious diseases. Also some non-infectious diseases like heart disease, chronic disease, Alzheimer, stroke, and kidney disease, chronic kidney diseases, and cancer. These are the non-infectious diseases, which is mostly this kind of non-infectious diseases is mostly responsible for the ourselves. But in this case of infectious diseases, it can be spread from the one person to another person. It can be easily spreadable. But in this case, the non-infectious diseases, it's the most dangerous, and it can be mainly identified by the, mostly we can identify at the end stage of the symptoms that cause severe infect. It also even causes death. So the current clinical dialysis mainly related to the laboratory results. For example, if we have affected some infections like some fever or something, we will go to the hospital and they are taking the blood or some urine, and then they providing the technician to analyze the results. Is either we can be affected or not affected. The mainly the 70%, and then doctor take the decisions we are affected or not. The mainly currently the 70% of medical decisions from the doctors are mainly depending on the laboratory technician, laboratory results. Mainly depends on the laboratory results, which will be the currently in wherever we go in wherever country, the laboratory results mainly predicts our the health medical decisions from the doctors. Mostly the current detection methods like in starting time the thin layer chromatography, that mainly in the gold standard test ELISA, and liquid chromatography and analytical gas chromatography and other electrochemical techniques. From that, those techniques are consuming the ELISA and some other liquid chromatography. These techniques need some well-trained technician, as well as it takes so much of time, more than 24 hours, and also it needs some special equipments, and the cost is very effective. The test cost is very effective. In the fact of the electrochemical sensors, it provides the real-time and easy to use and cost effective. It can be accurate, and the sensitivity and the concentration is more accurate. Currently, the portable, as we know, we can see in the market, we can easily find out the glucose meter and BP meter and uric acid meter. These are the portable chemical sensors, which are the mainly provide the quantitative results like number quantitative results, and other also the infectious diseases like pregnancy kit and HIV/AIDS and the COVID-19 kits. These kits are provide the some naked eye response from the, it gives the either it can be positive or negative. This can be the qualitative analysis from the some other infectious diseases. Also, Here nowadays we can find the market wearable physical sensors like smart watch, smart band. We can easily get from the Apple and Samsung. Those companies are producing this kind of smart band to determine to quantitatively analyze the body calories and heart rate and blood pressure and also oxygen levels and step count, and then also even in the sleep monitoring. Remote monitoring system. Sorry. Okay. This remote monitoring, health monitoring system, it's mainly producing that physical sensor, mainly giving the results about our physical activities of our body, like running or something, some other physical exercise. We can identify by this kind of calories, heart rate, this kind of in our body. Also, the various physical sensors, health parameters detected by the physical sensors, mainly temperature, heart rate, blood pressure, and oxygen level. Also, we can find out the electrical sensors like heart rate, electrocardiogram, and electrophenologram, and electromyography for muscles and brain. How also currently available the chemical sensors, the glucose, electrolytes, drugs, proteins, hormones and amino acids and lactates. Also, we can find the glucose and electrolytes and also some drugs and lactase. We can find out easily from the commercially available kits nowadays available, even though it's cost effective or effectiveness. But in the chemical sensors in our body, like proteins and hormones, plays the major role. But still, there is growing research is mainly focused on to detect the proteins and hormones in continuously, especially in the non-invasive technique. Non-invasive means which cannot give any pain. Like if we put the injection, it can be considered as invasive. If we cannot without injection or without taking the blood or some other invasive techniques, it can be considered as if it gives pain, it can be considered as invasive. It gives non-pain, it can be considered as a non-invasive determination. Here, the proteins and hormones, the detection of protein and hormones, the devices are very less, because the wearable in the proteins and hormones, it consists of our body. It's very, very low quantity in sweat and some saliva. Here, the wearable chemical sensors, like therefore, they are fabricating the minimally invasive, like microneedle based devices to detect the antibiotics and present in the alcohol, if we drink the alcohol and cocaine and some other, for the forensic studies for the devices, and also some industrial fluids, ISF, industrial fluids, and there is a ring type biosensors. However, the challenges of biosensors in the protein and hormones, it's very difficult. Proteins are the building blocks of life because of the most abundant molecules present in our body and form about 60% of the dry weights of cells. Also, on the another hand, hormones are the chemical messengers. They are nearly made by the endocrine glands and they travel in the blood. The signals of hormones, it's greatly affect the organs and tissues in different ways, and therefore the hormones are especially important for growth, metabolism, appetite, and sexual production. These are the. However, the detection of hormones and proteins, it's a quite challenge, because the proteins and hormones, they are surrounded by a peptide linkage. So the sensitive detection of these proteins and hormones, it's a challenging task. Therefore, the detection of these proteins and hormones, it's very important to create the device which must be more sensitive for the proteins and hormones. These are the simple mechanism, the proteins and hormones. So as a result, ultra low level detection of proteins as well as hormones is a major challenge. Therefore, the various researchers have been developing various sensors. So here we will briefly discuss about what are the sensors. Here is the basic principle of electrochemical biosensor. This is the analyte. This is the bioreceptor. This is the transducer. This is the electrode material. This is the bioreceptor like aptamer, antibody, or some enzymes. This is the analyte, which means our target like glucose, urea, ethanol, and cytokines and cortisol, these kind of proteins which from the analyte it attract from the bioreceptor, and while reacting with the transducer and which give the electrochemical signals, from which signals we can identify the identify the biomarkers present in our body, like our saliva or urine or blood or sweat. We can identify the concentration of the biomarker. Here the main drawback is drawback is to detect this kind of protein in the ultra low level. It must be there is a lack of connection between the analyte and the transducer. So therefore we are using the nanomaterial in order to overcome the issue of the electronic transition, like electronic communication between the target biomarker and our electrode surface to get the accurate detection. Here we can use the nanomaterials which can transfer the electrons to the electrode surface to the active biomolecule. Mostly the nanomaterials can be classified into different types: 0-dimensional, 1-dimensional, 2-dimensional, and 3-dimensional structures. Here we will bring the structures. It's mainly based upon the morphology of the material. Here we can briefly discuss about the 2D materials. These 2D materials have the significant advantage like stable and imaging potential, magnetic control, high loading capacity, high biocompatibility, high surface area, and even stretchable. Especially this currently the MXene, it has the more advantages like open 2D channel ion transport, the fast storage capacity, and compatible with flexible devices and stretchable. The small nanoflakes can be used as for inkjet printing of electrodes. MXenes was invented by Professor Yuri Gagatsky at Drexel University. It's a family of graphene-like 2-dimensional transition metal carbides and nitrides, and also which recently produced by the exploration of MXenes, so-called MaxSpace. Here, M represents the early transition metal, and A group element. A is a group element mostly in third group or fourth A group, and X can be carbide or nitrate. Unique combination properties of materials and metals and ceramics. These MXenes, here we can consider why MXenes not as a graphene. When compared to graphene, MXene has a strong van der Waals bonding between the layers, high electrical capacitance, can be easily prepared and moldable, and conduct heat and electricity like metals, and electrically stiff, strong, and heat tolerant like ceramics, chemically thermally stable, and also cheap, and are also fatigue, creep, and oxidation resistant. Here, this is the simple synthesis protocol of MaxSpace MXene, and which for the HF treatment, HF etching, and also it produce single layer and layered MXene selective layer etching layered mixing, and it produce single layer mixing sheets physically separated from mixing sheet after sonications. These are the SEM micrographs of different etching time and the etching images, SEM images. Also, these mixings are widely used in the sensor applications in strain sensor, pressure sensor, gas sensor, and also biosensor. And also it can be used as a wearing electronics, hand wearing electronic devices, and also head wear electronic devices and foot wear electronic devices. So from this, we can briefly discuss about the wearable sensor device for female hormone estradiol monitoring. Here we can see the female production of and the role of female hormone estradiol. As we know, the female hormones affect much woman's health from menstruation to pregnancy to menopause and more. For an example, even in the depression of women, it's mainly depend on the hormones, especially in estradiol hormones. They are regulated by the feedback of mechanism from the hypothalamic pituitary ovarian axis, which governs the female hormonal events related to the reproductive activity. Oestradiol is the primary form of female hormone estrogen and most potent and prevalent female hormone during the reproductive years. During the menstruation cycle, oestradiol provides a feedback about the hypothalamic pituitary and ovarian axis to regulate the production of luteinizing base hormone and ovulation. It can be mainly, we can see the how it forms from the estradiol hormone in different times, how it forms and gives the reproductive years, which mainly related to which most of the problems for women is mainly related to this hormone, for like ovarian problems and some other issues. These hormones is mainly responsible for the most of the problems here. Therefore, we developed a wearable sensor chip device for the monitoring of female hormone. Here, this is our sensor device integration. As we see before previously, this mechanism we can see in the following devices. This is our fabricated sensor device, which composed of the microfluidic layer and the wearable badge and the electrode and medical tab, which can be moldable in the ring type and so on. This is the scalable manufacturing of the disposable sensor badge by inkjet printing. Here, first we can treat it with the silver and then gold and then silver and carbon for the counter and then mixing to. This is the mass protection from the A4 sheet, like A4 sheet. Usually commercially we are using the OHP sheet. We are using the same OHP sheet as the substrate. This is the fabrication of microfluidic wearable badge from the PET sheet. Like we have PET sheet means that we have the like OHP sheet. It's a PET sheet. First we have treated with plasma, because in order to change the surface hydrophobic to hydrophilic, and then electrodes are the inkjet pattern and the estradiol sensor fabrication. And then on another hand, this automation of accumulation layer of its medical tab, then we cut it into in separate place, and then biorecognition interface, AE nanoparticles and PET, and then collection layer, and then assembled microfluidics, and then this is the assembled estradiol. This is the sensor electrode badge, which can be from this medical tab. We can attach in our hand or something, in our arms, in our chest. We can attach this sensor batch, and also this sensor batch which is connected to the circuit, flexible printed circuit boards, which contains Bluetooth and battery and boost converter, and then BLE module and electrochemical analog front and voltage regulator. If we can connect with this, our sensor, this sensor electrode, it can be connected to the flexible printed circuit board, which contains the Bluetooth and everything, battery and everything. These are the SEM-TM images of MXene and also XRD and Raman spectroscopy images, confirmation of the MXene and forming the MAC space to MXene. Also, this is the crumpled sheet-like structure of MXene ink. The key factor of this sensor electrode is the biorecognition interface modified with estradiol selective DNA aptamer, which combined with gold nanoparticle and MXene as the working electrode with the capture single standard DNA for indirect detection. This wearable sensor device contains microfluidic iontophoresis patch, pH sensor and temperature sensor and impediometric ionic strength sensor, as well as electronic circuit and wireless communication, as we seen the previously before. Here, the simple mechanism of the aptamer based DNA aptamer, single standard DNA ostradiol aptamer at the gold electrode surface. From the aptamer, we can 3N and 5N, 3N methylene blue as the redox probe, and which can be used as the redox probe. Here we can see that if it stands with the displacement of the ostradiol, it can be the AUS bond can be formed, which can be captured at the ostradiol aptamer hormone, and then producing the signal output. Then methylene blue can be released. At the biorecognition interface, the ostradiol aptamer DNA is immobilized on the gold nanoparticle surface, forming a partially hybridized duplex with methylene blue single standard DNA probe molecule, which acts as a competitive probe. This is the schematics of the detection. Also, the recognition of estradiol molecule by the aptamer recognizing interface. This is the target recognition induced displacement of methylene blue SS DNA and a recapture of the released methylene blue SS DNA by the thiolated SS DNA and the working electrode. This is the electrochemical quantification of the methylene blue recaptured from the DNA and the working electrode. This is the simple, we can identify the easily mechanism how the aptamer can be located at the react with the electrode surface. These are the gold, this is the gold nanoparticles, inkjet printed gold nanoparticles. Of once we dropcasted into the aptamer, it can form the AUS gold thiol bond, thiolated aptamer, and then MCH blocking, which can be used to mecaptohepsanol. This can be used to the unblock the active sites of the electrode surface. And also here, inkjet printed gold nanoparticles and with MXene, and then aptamer, thiolated aptamer adsorption, which can be formed the AUS bond, similar to the MCH blocking. This is the used as the working electrode, and the detection working electrode, the thiolated DNA molecule and antisense strand with methylene blue standard DNA probe molecule and immobilized in A nanoparticle MXene electrode. In the presence of ostradiol, the aptamer, which have the higher affinity towards the ostradiol than the particularly hybridized sequence. This is the electrochemical studies. Here we can see that the gold nanoparticle combined with MXene shows a highest peak current when compared than pristine gold nanoparticles and gold on MXenes, and this DNA, thylated DNA. These are the impedometric analysis studies which directly depends on the these different materials. Here we can see that the square wave voltammetric response of aptamer ostrodiol sensors in artificial sweat, the concentration of 0 to 100 picomolar of ostrodiol. Here we can see that the concentration of ostrodiol increasing and the peak current was increasing in the reduction side. Here we can observe clearly. So from this graph, we can put in the linear plot, we can find out the limit of reduction is 0.4114 picomolar level reduction of ostrodiol in artificial sweat. Also, here from the sweat entry and sweat color, this is the microfluidic device. This when combined with microfluidic device, you know it has the sensor device doesn't have the decrease in the sensitivity and selectivity when operating in the microfluidics. Also, it doesn't show the another similar kind of interferent with another similar kind of hormones like progesterone and folic acid and serotonin and cortisol and other some glucose, kanamycin and lactic acids. This is the validation of aptamer sensor towards the ostrodiol quantification in the iontoporosis induced human samples. Here also it can be rotatable and easily moldable, which can be attachable at any part of our body. Here we can see simply see how the sweat can be coming from the iontoporosis electrode. Here we can see this electrode. This is the iontoporosis. While applying the voltage, the sweat is formed, and then this is the inlet and outlet. From this electrode, this working electrode can identify the target ostrodiol hormone. Also here we can find out the excellent selectivity as we discussed about the mexin and gold nanoparticles combinations. It can be attributed to the both gold nanoparticles and mexins play a crucial role in the sensor performance when combined with the plain gold electrode as well as the gold nanoparticles. Here from this in the study we prepared this mexining which for the delamination of MagSpace titanium aluminum carbide, the lithium fluoride and HCl. We used ethylene glycol water in 1:1 ratio, and we developed 4 layers to prepare our sensor working electrode. Here the mexin shows the 40% signal enhancement was obtained to the additional mexin layer, which is due to the high electrical conductivity, which facilitate the electrode conductivity and the efficiency of charge transport and transport for the reduction of methylene blue molecules. The importance of mexin further validated by the incorporation of 2-mercaptanopropionic acid to block the surface of mexins. Here we can identify that without mexin, it doesn't show it shows the electrode shows the only less than 40% signal enhancement. Here the mexin produce 40% signal enhancement, which is due to the ultra high electrical conductivity and also charge transportation. Here from the real samples we can identify the growth of female hormone from the menstruation to ovulation and the luteal phase. Here the 32 years old female and 28 years old female. Here we can see that in 14 days the hormonal level was very high, and then it was decreasing, and then after this is a second cycle. After from the second cycles around 40 days, 42, it shows the highest estrogen hormonal levels. Here it might be due to from the ovulation as well as ovulation. That means the growth of egg growth timing. I think the luteal hormonal stage, luteinizing hormone from this, the directly calculated from the detected from the wearable sensor batch. These are the different participants can be analyzed from the woman participants, analyzed from the hormonal level. Here you can see this real-time wireless hormone monitoring. This is the estradiol of this is the sensor electrode. From this, we can identify the estradiol hormonal level as well as our body pH as well as our body temperature from this sensor. Also, the sensor exhibited excellent stability even after the 500 repeated cycles in the BBS. This is the square voltammogram of cycle 1 and cycle 5000. It only shows a very small decrease in the current response. Also, the repeatability and storage stability of the aptamer estradiol sensor. The peak current has the highest height of the square wave voltagrams in the estradiol sensor from the 5 different batches. It's also show the very good batch to batch variation, and also it shows the very good response in the 16 days. And also the sensor regeneration. Here it can be clearly shows that the regeneration of sensor before incubation, after incubation, regeneration after re-incubation from the number of regenerations. This is the mechanism of the in vitro sensor regeneration process. This is the biorecognition element. This is the methylene blue. After wash, the methylene blue is removed, and then it can be entered into the another place for the regeneration purpose. As to the selectivity in the microfluidic device, it's also showed the very good, highly selective towards the estradiol hormone. In the summary, we have developed the aptamer nanobiosensor with sub-picomolar sensitivity for the estradiol in sweat using gold nanoparticle machines and integrated with the wireless system with also the iontophoretic gels and microfluidics and functionalized sensors, enabled the automatic and on-body monitoring of estradiol levels, found the direct correlation between the sweat and serum, and also device supports at home hormone monitoring and can be adapted for the other biomarkers in the personalized medicine in future. Thank you for your attention.
Thank you so much, sir. We
Thank
now
you.
move into the interactive segment. Participants, kindly unmute and ask your questions to the speaker. Participants, if anybody having queries, sir, a question from our side. How promising are aptamer gold nanoparticle sensors for early detection of hormone-related disorders in women health, sir? Hello, sir.
Hello, ma'am. Audible?
Sir, audible,
Okay.
sir.
Yeah.
Sir, this aptamer gold nanoparticle sensors, how effective in early detection of hormone-related disorders in women health, sir?
Actually, ma'am, aptamer we have specifically designed for the estradiol hormone. As we discussed in this, estradiol hormone, it's mainly related to the woman's health, like ovulation, from menstruation to ovulation, and ovulation to menopause and everything. So, particularly depending upon the structure of the estradiol, we can design the aptamers like amine terminated aptamer or thiol terminated aptamer, in which the SH group of thiol, which can be connected to the, while interact with the gold nanoparticle, it forms strong the gold AUS bond. AUS bond, which can be very strong, so it can be easily, particularly capture the estradiol hormone only without any other hormones. With doesn't detect any other hormones.
Thank you, sir. It also overcome the interference of biomolecules also, sir. In blood,
Yes, ma'am.
some biomolecule.
Yeah. It doesn't interfere with some other biomolecules because the aptamer have the high selectivity towards the target hormone. We have specifically designed this aptamer towards for the target hormone only. So even though the relatively potentially co-interfering some other, like cortisone, the cortisol hormone, it's also related to the stress. It's a stress biomarker, even though it doesn't show the any significant impact in the sensor device, ma'am.
Sir, what is the minimum reduction limit of such sensors, sir, for female hormones?
Actually, in every hormone, it depends. In saliva, there has been some limit. Also in blood, it's very, for an example, if we have the glucose in our body, if we take the blood test, it shows, for like example, it's 1 mg. While we are taking the saliva, if we do the test, the saliva glucose is very low. The World Health Organization about this hormone level is maybe, if it exists in the 300 picomolar, maybe it's considered a serious problem to the health issues. 300 picomolar.
Thank you, sir. Is there any questions from the participants side? Sir, one final question, sir. Can these sensors be adapted for home-based that kits something we are using? Is it adaptable for that, sir?
Yes, ma'am.
Home-based diagnostic kits like commercially available.
Yes, ma'am. Actually, as I told now before, the problem of the hormones and the proteins is covered by the peptide linkage, which mostly the sensitivity, the range is the hormone in present in the saliva, in our urine, and then some our sweat. It's very, very low concentration. Therefore, so many researchers, they are developing this kind of proteins and hormonal sensors. Maybe after 5 to 6 years, maybe it will be available in the market, I think.
Okay, sir. Sir, one more query in that chat box. What is the lifespan of the sensor and the reliability of the values? One faculty is asking.
Yeah, as I told, in 16 days, it showed very good response in our device. After 16 days, the response will be low, so we can regenerate the aptamer. Directly we can regeneration the aptamer with that's why we use the methylene probe redox probe, and then we can use the regeneration.
Thank you so much, sir. It seems there are no further questions. We can conclude the query session. So we sincerely thank our speaker for taking the time to answer each question so thoughtfully and clearly. Your insights on wearable biosensors have shown us how simple a device can become a lifeline, extending care beyond hospitals and making health monitoring a part of everyday life. We are truly grateful for this futuristic perspective. Thank you so much, sir. Sir, one more request. Can you switch on your the participants? Kindly switch on the video for photograph. Sir, kindly stop your slide sharing, sir.
Okay.
Participants, kindly on your video. Gratitude is the sweetest flower that blossoms after every fruitful session. Just as every flower adds its own fragrance to your garden, every effort and contribution has added beauty to this program. To present this bouquet of thanks, I warmly invite Professor Dr. S. Sivagami ma'am, Head of the Department Science and Humanities, to deliver the vote of thanks.
Good afternoon to all. As we come to the conclusion of this 5-day International Faculty Development Program on recent trends in chemical science and engineering, it's my privilege and honor to deliver the vote of thanks on behalf of the Department of Chemistry, New Prince Sri Bhavani College of Engineering and Technology. At the outset, I extend my deep sense of gratitude to our respected chairman, Thiru K. Loganathan, and Vice Chairman Thiru L. Naveen Prasad for their constant encouragement and visionary support in all our academic endeavors. My heartfelt thanks to Professor A. Swaminathan, Director, and Dr. T. Saravanan, Principal, for their valuable guidance and motivation that made this program a reality. A special words of appreciation to our organizing team, Dr. C. Sabarinathan, FDP coordinators and co-coordinators, Dr. G. Aida and Dr. M. Muchida, for their tireless efforts and seamless coordination throughout the program. Now, I would like to place on record our sincere thanks to our distinguished resource persons who enlightened us with their expertise. Dr. Srinivasan Hariharan, University of Amsterdam, Netherlands. Thank you, sir, for setting the right tone on day one with your profound insights into quantum chemistry, with open new perspectives for our faculty and researchers. Dr. Vinuta Vishnukamath, Sagar College, Bangalore. We are grateful to you for day two engaging session, which blended clarity with the depth and helped us related to the silver nanoparticle from neem involved reducing and capping agent and many other uses. Dr. Makesaki, Agati College of Engineering and Technology, Karnataka. Thank you, sir, for your enlightening lecture on day three. He provided phenolium-based fluorescent molecular rotor used as sensor to detect changes in cellular microenvironment. Dr. Babasaheb Motsaha, National Taiwan University, Taiwan, on day four, your scholarly presentation on writing a papers in journal gave us insights and encouraged participants to think beyond conventional approaches. Dr. Jairaj Vinod Kumar, University of Sugopa, Japan, your concluding session on day 5 has been truly inspiring, highlighting advanced materials research and offering a forward-looking outlook for young researchers. Thank you, sir. We are proud to have nearly 250 participants registered for this FTP, making a grand success. Thank you all participants for their active engagement. I hope this program has been informative and enriching for everyone. Let's continue to apply the knowledge gained to advance our research and teaching practices. On behalf of the organizing team, I once again thank you each and everyone for you making this event a grand success. Thank you all.
Thank you so much, ma'am. Feedback link is posted in the chat box. Participants kindly fill it and submit it. So finally, over these days, gratitude has blossomed like a flower, fragrance spreading from one session to another. Every idea shared was a petal, every discussion a ray of sunlight, and together they formed a garden of wisdom. This day is not only the last login of our FTP, but the beginning of many logins into new ideas, new research, and new collaborations. As we bid adieu to this journey, Let us carry the fragrance of learning, the colors of collaboration, and the seeds of inspiration into our future endeavors. This FTP may conclude today, but its blossoms will continue to brighten our path for years to come. Thank you all. Thank you all the participants for your consistency in participation. Thank you so much.
Ma'am, shall I close my window?
Sure, sir.
Thank you
Thank
so
you
much.
so much, sir. Thank
you
you
so
for
much,
spending
ma'am.
your
Thank
valuable
you.
time for us, sir. Thank you.
Thank you. Thank you. Have a great weekend.
Thank you, sir.
Thank you, sir.